You're in the home stretch. We are almost done with this project. Project 1E is, again, it's just a modified version of 1D. Okay? Again, you're only actually adding a few lines here to Project 1D. So if you got 1D to work, you're going to get Project 1E. 1E is the final question. The big overarching theme of this whole module. Given a latitude of a location and a longitude location, and given that azimuth angle for the panel, which we're going to assume is south, tell me what the panel elevation angle is that produces the most energy over the course of a year. If your panel has to be fixed, like those panels out in the faculty parking lot at Creighton, what angle should you make them to generate the optimal amount of energy over the course of a year? Now, I just kind of throwing up here, this is from the previous one. This is sort of the basic wiring diagram of your Project 1D, where we were computing the angle that made the maximum power on this day. Now what we're going to do is we're going to expand that idea and say, okay, at this angle, let me try all the days of the year. So for every one of the 365 days of the year, I'm going to compute the total amount of energy per square meter that the panel can produce. And I'm going to just add that up from day 1 to day 365. That's what that total annual total energy at this elevation is. We started off with 0, and we're just going to, at this elevation, we're just going to try, okay, we got the panel at 10 degrees. Run it for at 10 degrees of elevation off the horizon. Run it for day 1 all the way to day 365. Every day we're going to integrate the total amount of power and then add that up to this running sum. So that by the end of the year, we now have the total amount of power, that of energy that per square meter would be generated, or at least incident upon our panel. All right. So now at that angle, we know what the total amount of energy would be. All we got to do now is figure out, is that the maximum amount? Okay. So we have the same kind of trick we had before, where we're just keeping track of, okay, now at the next angle, and the next, is that more than we saw before? If so, then replace our max energy is now this angle, is now this amount of energy, and the angle that produces that energy, elevation for max energy, becomes this panel angle. It's actually pretty slick how this works. I mean, it's really just this inside little loop here. It's a nested loop. We have this outside loop that is saying, okay, for every angle. Now, at the current angle, we're going to do that calculation for all 365 days and add up the total amount of energy. Woo! Pretty neat. This is a good time to reflect upon the difference between a compiled language and an interpreted language. An interpreted language is like octave. This is going to take a while. If you just ran this program as I have it here, it's going to take about an hour to run. Because this is a lot of math for an interpreted programming language. I mean, yeah, when you just computed the total amount of energy on one particular day at one particular angle, oh, it took maybe a second or something. You hit enter, and by the time your fingers were clear of the keys, the program was done. On the last part 1D, when you were computing it for all those angles, you might have noticed it took like 10 seconds or something for the program to run. Now you're doing it for all these angles for 365 days of the year. It's going to take about an hour for this thing to run. Don't do that to yourself. I mean, every time you run this thing, you want it to take 365 days. I'm sorry, do you want to take it like an hour? And, oh no, it didn't work. I got 0 for an answer. I got not a number for an answer. That's not good. This is a pain. Interpreted languages are just not fast at this kind of thing. This thing would run in a fraction of a second in C, but in octave, it's going to be slow. So I'm going to give you a suggestion on how to make this go faster. See how I changed the loops there? Instead of going from 10 degrees to 90 degrees in 1 degree steps, let's go in 10 degree steps. So we'll do it at an elevation angle of 10, 20, 30, 40, up to 90. Look at that. We've reduced the amount of time this will take by tenfold, right? Similarly, my Julian day, look what I did here. I made it go by 30s. So we're going to do it at Julian day 1, Julian day 31, Julian day 61, or whatever. Do you know why we can get away with this? Because this will make the program run faster. Okay, it will. If it can produce an answer for this, it can produce an answer with the set back down to 1, where now you're going in 1 day steps and you're going in 1 degree steps. Now, having messed around with this a little bit, let me make a suggestion. Don't run this thing with 1 degree steps, and don't run Project 1E with 1 day steps. You don't really need to, and it's going to be frustrating for you to make this thing run for like an hour. Instead, once you have the program tested and you know how to, and it works and it's producing good answers, you know, let's say you get that the optimal elevation angle is 45, you get it 40 degrees. Okay, now, well, that's just because it only moved in 10-degree steps. Now, go back and change it so that we're moving in 1-degree steps, and you'll find out like the optimal angle is 43 degrees or something like that. That's cool. As far as the Julian day, though, goes, you don't really need to do it for all 365 days of the year. Here's the deal. Whatever angle we come up with as our optimal angle, that is the optimal angle, whether we're talking like the total amount of power added up on all 365 days of the year, or if that would also be the angle that produces the most power if we're just saying the optimal amount, the amount of power, the sum of the amount of power on, say, all the Mondays, or every 10th day or something like that. So like if you had from 1 to 365 in steps of 7 days, where like you're effectively doing like, okay, this is 1 day this week, 1 day the next week, whatever sun angle produces the most power for that is also going to be the sun angle that produces the most power for every day. So, you know, I would recommend running it once you get it working, where the panel elevation angle does move in steps of 1. I'd really like to see that like the optimal angle is 43 degrees or 57 degrees or something like that. But you don't have to make it run every single day of the year. If you want to do it like, you know, every 14th day or something like that, 1:14:365, so that you're not, you know, that will speed your program up by a factor of 14. I'm all in favor of that. I don't think there's any reason to sit there and watch the thing chew on this. Alright, how do you know if it's working? Well, use Evansville's numbers, and if you do it, you'll get 55 degrees. Okay? Yeah. Go ahead. I think it's kind of fun. I think it'll be interesting to see if we can maybe at some point compare it to what the panels actually are like out in the faculty parking lot. How bad is this? Again, my version ended up with 77 working lines. Almost every single line of that program comes from 1D, or it's something I just literally gave you in those slides just before. It shouldn't be that big of a deal to get this thing working, and like I said, I feel a little bad if I made you write 77 lines from scratch, but you're mostly just working with code you already have working, you've been building, and so this shouldn't be the worst thing you've ever had to work on. The deliverables, modify the program so that it works for your city's latitude and longitude, and then submit the program to me using Turnitin. When you are ready to, also email me what you got for the optimal elevation angle for the panel according to your program. Because I have ways I can check your answer. Alright. After this, you're all done with this module. There's no tests or anything in this module. It's just a project. Please let me know if you have any questions, and good luck.